Oxygen, yes. Ozone is rare.
And when it is present, what is it considered? Remember chapter 2? Ozone is an air pollutant in the troposphere. And the main source of ozone in the troposphere is from automobile exhaust. And so remember, in the hot engines of the car, oxygen can react with each other. Oxygen molecules can react with each other and therefore produce ozone. And then it exits the tailpipe of the vehicle. Catalytic converters can help cut down on this reactivity in your engine. But some ozone does exit your tailpipe. And so in the troposphere, it is an air pollutant. What about the stratosphere? Do we have oxygen in the stratosphere? Remember we talked about UVA, UVB, and UVC types of UV radiation last week. We said in the stratosphere that UVB is not as strong in energy as UVC, and therefore UVB can only be absorbed and break the bonds in ozone, but UVC is the highest energy of all those three, and it can absorb and break the bonds of both ozone and oxygen. So yes, there is oxygen in the stratosphere, but do we have more oxygen in the stratosphere or the troposphere?
The troposphere.
Right. So yes, but in a smaller concentration than in the troposphere. And then, of course, yes, we have ozone in the stratosphere, and it's at a higher concentration than in the troposphere. And in the stratosphere, that ozone is very important in protecting us against UVB and UVC radiation. And so I already answered that question. Number 2. So ozone has the ability to absorb both UVB and UVC. Any questions about numbers 1 and 2? So we said that ozone has a strong odor, and the odor of ozone can be detected at levels as low as 10 parts per billion. So would you be able to smell ozone in either of the following samples? If you have 0.118 ppm of ozone detected in LA, could you smell it?
No.
No,
And why not?
because it's a smaller amount than 10 parts per billion.
So 10 parts per billion, the parts per billion is an apple. This parts per million is an orange. Can I compare an apple and an orange?
No.
Did you convert this to parts per billion? In order to make the comparison, they have to have the same unit. So did anyone convert 0.118 ppm to parts per billion? Did anyone do that? See, these are the types of questions that you got to use your critical thinking skills. Every question is just not going to be just explicitly, let me plug in these numbers and let me spit out this answer. You have to think about the question. So I'm not sure until I convert this guy to ppb. And then if it's greater than or equal to 10 ppb, then yes, you would be able to smell it.
Would it be 118 parts per billion?
You are absolutely correct.
So you would be able to smell it.
Yes, you would. And the reason why? Remember our conversion factors, converting between ppm and ppb that we learned in chapter 2? We have to continue to apply things that we learned in a previous chapter. We just can't forget about it. So that's 118 ppb. So yes, you would be able to smell that ozone. What about 25 ppm? Again, we've got to convert it to ppm.
25,000.
Very good. So that's a very high concentration because that's 20 kilometers above the Earth's surface. So where would we be? Look at that. We'd be in the ozone layer. So of course, in the ozone layer, we should have a high concentration of ozone that we can detect. And we're doing the same conversion that we did in part A. And so we get 25,000 ppb. So yes, we will be able to definitely smell that. Any questions about number 3? And so question 4, describing 3 differences between the air in the troposphere and the air in the stratosphere. Consider concepts in both chapters 2 and 3 to answer this question. So what's going to be a difference between the air in the troposphere and the air in the stratosphere? So one thing that we can say is that the air in the troposphere is more dense. We know that density is the number of grams per milliliter. And the reason why the troposphere air is more dense is, can someone give me an idea why?
It has water. It's humid.
Yes, the air in the troposphere has water vapor in it. It also has nitrogen, it has oxygen, it has argon, it has CO2. So you've got lots of different, and it's got all the different air pollutants that we put in the air too, right? So in the troposphere, we've got more stuff in the air. We've got a variety of different atoms and compounds in a given volume. So the amount of mass per given volume in the troposphere is much greater than in the stratosphere, because in the stratosphere, all you have is oxygen and ozone. But in the troposphere, you've got oxygen, you've got nitrogen, you've got argon, you've got CO2, you got water, you've got ozone and the rest of the other air pollutants that we put in the air. So the troposphere air is more dense. And so the troposphere is going to have a lower concentration of oxygen and ozone, whereas the stratosphere is going to have a higher concentration of O2 and ozone. Because remember from chapter 2, in the troposphere, only 21% of the air is oxygen. But in the stratosphere, it's going to have a higher concentration, more of like 30 to 40%. And then the rest will be ozone. Whereas in the troposphere, your ozone concentrations are very, very low. And so the troposphere, it contains your air pollutants. like SO2, SO3, NO2, so on and so forth, air pollutants do not reach the stratosphere. So those are three differences between the air in the troposphere versus the stratosphere. Any questions about number 4? And so we've been talking a lot about ozone and UV light. So now we're going to shift gears and talk about Lewis structures. Our lab this week is a Lewis structures lab. And so in order to draw a Lewis structure, the first thing that we would need to analyze about the molecular compound, and we said that molecular compounds contain only nonmetals, is that we've got to know the total number of valence electrons in the molecule or molecular compound. And so only a limited number of electrons can reside in the outer energy levels. And it's the electrons in the outermost energy level that participate in bonding. And so when two atoms in molecular compounds, the case is two nonmetal atoms, when they are joined together and they form this molecular bond, which is also called a covalent bond, only the electrons that lie in the outermost energy level farthest away from the nucleus, only those electrons will participate in bonding. And so how do you know how many valence electrons that a particular element has? Well, you go by the group number. So for example, group 5A elements have 5 valence electrons. So if we take a quick look at the periodic table, the old way of numbering the groups were just numbers 1, 2, 3, 4, 5, 6, 7, so on and so forth, all the way to 18. But then once the periodic table evolved and the classification of the elements was more clear, then they changed to the Roman numeral designation of group numbers. And that's the modern way to designate the group numbers, is by the Roman numeral format versus the regular numerical format. And so when we start here with the transition metals, and the transition metals end here, you note that the Roman numerals become accompanied with the letter B. So the letter B next to the Roman numeral lets you know that you're dealing with a group that's within the transition metal specific area of the periodic table. But then outside of this transition metal block, you see the Roman numerals next have an A next to them. And so you have group 1A, 2A, and then you jump all the way over to where the nonmetals are. And that's where you start 3A, 5A, 7A, and 8A. And so the Roman numeral number is going to tell you how many valence electrons that the elements in that group have. So group 5A, as we mentioned earlier, nitrogen, phosphorus, arsenic. All of these elements in group 5A have 5 valence electrons. Your noble gases in group 8A, they have 8 valence electrons. And having 8 valence electrons means you have a full octet. And that means that the outermost energy level for these noble gases in group 8A that outermost energy level is completely full. The outermost energy level can hold a maximum of 8 electrons. So the noble gases are stable. And that's why noble gases are often referred to as inert. Inert means non-reactive or stable because they're happy. They already have a full octet. Their outermost energy level is already completely filled with electrons. So it doesn't need to lose any electrons, nor does it need to gain any electrons because it already has a full octet. And having a full octet is stable, it's happy, it's not going to lose any electrons. And because it's already happy, it doesn't need to gain any electrons either. So that's the goal of all of these other elements in groups 1A, 2A, 3A, 4A, 5A, 6A, 7A. They want to form a covalent bond, and in this covalent bonding, they'll share electrons with another element. And in the sharing of electrons, each of those elements that are a part of that covalent bond, they're sharing electrons with each other. They can complement each other and reach that full octet of electrons. And we demonstrate this by drawing the Lewis structures of the molecules and compounds to show how the covalent bonds are formed and how these atoms or elements are sharing electrons with each other. So the atoms are going to react with each other in order to completely fill a shell of electrons. And that means they want to have 8 electrons or a full octet. And that's called the octet rule. So to meet the octet rule of a stable set of 8 valence electrons, electrons are shared between 2 atoms. And in the sharing of electrons, a covalent bond is created. And covalent bonds are only found in molecular compounds. So, Lewis structures, they're also called dot structures, and they are representations of molecules or molecular compounds. And you have demonstrated the sharing of electrons. So what are the rules for drawing Lewis structures? The first step is to count the total number of valence electrons in a compound by counting and adding up the number of valence electrons that are represented by each atom that's in the molecule. Then you add all the valence electrons that's contributed by the individual atoms to attain the total number of valence electrons. And then you want to arrange the atoms by placing the atoms closest to the left bottom of the periodic table in the middle. That's going to be your central atom in your Lewis structure. So whichever atom in your molecule or compound is closest to the left bottom part of the periodic table, that atom will most likely be your central atom. So the atom that's farthest to the left will be your and closest to the left-hand side and closest to the bottom of the periodic table will more than likely be your central atom. But one rule is that hydrogen will never be your central atom. Hydrogen will always be on the outside. And so you'll arrange all the other atoms in the structure on the outside of the central atom. And we call those other atoms that are not the central atom, we call them peripheral atoms. And then you want to place electrons as pairs of dots on atoms until their octet rule is met. And so 2 dots represent 2 electrons, which is a single covalent bond. So it takes 2 electrons to make a single covalent bond. And when you're placing the 2 dots around the atoms, you'll place 2 dots at a time, and you'll start on the outside or peripheral atoms first. And then another rule is that hydrogen only needs 2 electrons. Hydrogen is one of those elements that don't need to have 8 electrons. So hydrogen is an exception to the octet rule. And therefore, then if necessary, you may need to form double or triple bonds. A double bond is 4 electrons. Or you may even need to form a triple bond. A triple bond is 6 electrons. So only after you've assigned all electrons, and then if one or more atoms still does not have its octet satisfied, then you may need to form multiple bonds. And the multiple bonds are your double bonds and your triple bonds. And so also, instead of using 2 dots to represent a single bond, you can just use a dashed line. And then 2 dashed lines is a double bond. 3 dashed lines is a triple bond. So now let's put the rules to practice. So never on a test will you be asked to memorize and spit out these rules. I'm not interested in you memorizing these rules for memorization purposes, but you do need to know these rules so that you can apply them. Okay? And so let's practice drawing some Lewis structures. So the first compound we have is HCl. And so if we go to our periodic table, hydrogen is in group 1. So hydrogen has 1 valence electron. Chlorine is in group 7A. So it has 7 valence electrons. And so I always like to do my bookkeeping for my valence count. Hydrogen, 1 valence electron, and there's only 1 of them in the formula. Chlorine has 7 valence electrons, and there's 1 chlorine in this formula. So I have a total of 8 valence electrons in this molecule. And so I'll connect the hydrogen and the chlorine with a single bond. And that represents 2 of the 8 valence electrons. So remember, a single covalent bond is 2 electrons. And we can represent a single bond with this dashed line. So that single bond is representing 2 electrons. But I need to put in 8 valence electrons total. So like my rule says, I'm going to place electrons as pairs of dots around the atoms until they meet the octet rule. But we said that hydrogen is an exception. It only needs to have 2 electrons around it. And so there is the single bond. That single bond is 2 electrons. So hydrogen is fine. It is happy. It has 2 electrons around it already. But chlorine is not happy because it only has 2 electrons around it and it needs 8. So therefore, We'll put 6 electrons around it as single dots. And we'll put them in pairs of 2. So now chlorine has 2, 4, 6, 8 electrons around it. So now the chlorine's happy, the hydrogen's happy. I've got 2, 4, 6, 8 total valence electrons in my structure, and that's what I'm supposed to have. The octet rule for chlorine is satisfied, hydrogen being an exception to the octet rule, only needing 2. So hydrogen is also happy. So next, let's go to Cl2. We already said chlorine has 7 valence electrons. It's in group 7A, and there's 2 of them in this molecule. So that gives us 14 valence electrons for Cl2. So we put the 2 chlorines next to each other, and we connect them with a single bond. So that single bond, again, is 2 electrons, but we need 14. So again, we're going to put pairs of dots, 2, 4, 6, around each chlorine, 2, 4, 6. Now each chlorine has 8 electrons around it. The single bond itself is 2. Now these electrons that are not connecting this chlorine with any other atom, these are called lone pairs of electrons. These lone pairs of electrons are also called non-bonding electrons. This dashed line, that represents a single bond. So it's a bonding pair of electrons. That's a single covalent bond. So these are bonding electrons. Remember that single line represents 2 electrons. So that's the difference between a bonding pair of electrons and a non-bonding pair of electrons. So the same thing here with the Cl2. These lone pairs of electrons, they're non-bonding. They're just sitting on the chlorines, just sitting around those 2 chlorines, but they're not connected to any other atom. Only this single covalent bond here is connecting those 2 chlorines together. These other lone pairs of electrons are just sitting on that particular atom. And so I do my count, 2, 4, 6, 8, 10, 12, 14. I've met my valence electron requirements. Next, we have water, H2O. We've already looked at hydrogen. It's in group 1, so it has 1 valence electron, and there's 2 of them in the formula. So that's a total of 2 valence electrons provided by the 2 hydrogens. And then oxygen. And so at this point in the class, you want to have a periodic table handy while we're doing lecture, and definitely while you're doing your homework and quizzes, because you're going to have to refer back to the periodic table often. So it's a good idea to find one that you like. If you like the ones that are in our notes, this is from our chapter 2 notes. And just print you one out and have your periodic table handy, especially when you're getting ready to take your midterm at the end of this week. You definitely want to have a periodic table printed out and handy. So oxygen is in group 6A. So oxygen has 6 valence electrons. And there's only 1 of them in the formula for water. So water has a total of 8 valence electrons. And I always abbreviate valence VAL. And I abbreviate electron with an E and a negative sign. So that's my little shorthand work. And so these other two were pretty easy because they only contain two different atoms. You know, HCl, just a hydrogen and a chlorine. Cl2, just two chlorines. But now with water, I've got two hydrogens and an oxygen. So now comes the question of the central atom. Which atom will be the central atom? Will it be one of the hydrogens or will it be the oxygen?
Oxygen.
Very good, because oxygen is further to the left on the periodic table than hydrogen. So oxygen is going to be your central atom. So we'll put oxygen in the middle, and then we'll use a single bond to connect the two hydrogens, which are called our peripheral atoms, connecting those two peripheral hydrogen atoms to our central oxygen atom. And so again, our exception to the octet rule, hydrogen, it only needs to have two electrons around it and the single bond representing two electrons. So each hydrogen has that single bond next to it. So the hydrogens are happy, but the oxygen is not happy. Each of these single bonds is two electrons. So we've put in 2 4 electrons so far, but we need to put in 8. And the oxygen's not happy, so we need 4 more electrons. So we'll put them as lone pairs around the oxygen atom. So now the oxygen atom is happy. It has 8 electrons around it. 2 4 6 8. So now we are getting to our air components, oxygen and nitrogen. Those are the two major components of air in the troposphere. Again, we've already looked at oxygen. We said it's in group 6. And in O2, there's 2 of them. So there's a total of 12 valence electrons. Nitrogen is in group 5. So 5 valence electrons, and there are 2 of them. So for N2, there's a total of 10 valence electrons. Ozone, oxygen, is in group 6, and there's 3 of them in the structure of ozone, so that's 18 valence electrons. Ozone, as we said earlier, is an air pollutant in the troposphere, but it is very, very necessary in the stratosphere to protect us from UVB and UVC radiation. So first, let's draw the O2 Lewis structure. We'll put the 2 oxygen atoms side by side, connect them with a single bond. So we've put in 2 of the 12 required valence electrons. And so we follow our rules and we satisfy the octet rule for each oxygen by placing 6 dots in pairs of 2 around each oxygen. So would you say that my Lewis structure now is correct? Do I have 12 total valence electrons in my structure?
Yes.
2 4 6 8 10 12 14. I'm counting 14. Did you count the single bond as 2?
Yeah,
Don't
there's
forget.
too many.
2 4 6 8 10 12 14. Does everyone agree that I've put in 14 electrons?
Yes.
So is my Lewis structure correct?
No.
No, I don't need but 12. So this is our first uh-oh scenario. So uh-oh, what do I do to fix it? This is what we do to fix it. So what we're going to do is write ourselves a rule. So what is my problem? I've put in too many. So this is our rule. If we have too many electrons, and that's our case, we've got 14, but we only need 12. erase 2 sets of lone pairs and replace them with a double bond between the 2 atoms. So here's where multiple bonds come in. So it doesn't matter which 2 I erase. I'm going to erase those 2 and those 2, and I'm going to replace them with another single bond, giving me now a double bond between those 2 atoms. Now, how many electrons do I have?
12.
Remember, right, now I have 12. Each of these lines count as 2 electrons each. So now I've got a double bond, which we said a double bond is 4 electrons. Each of these lines represents 2 electrons. So 2, 4, 6, 8, 10, 12. Is each oxygen happy? What do I mean by is each oxygen happy?
Do they all have, or they both have 8?
Very good. So whenever I ask you, is this atom happy? That means, is this octet satisfied? Does it have 8 electrons around it? And that is true for each oxygen. Each oxygen has 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, and 8. So each oxygen has 8 electrons around it. So the octet rule is each oxygen, and my total valence electron count is 12. So now my O2 Lewis structure is correct. Now let's take a look at N2. We need a total of 10 valence electrons. So I put my 2 nitrogens side by side, connect them with a single covalent bond. So I've put in 2 electrons so far of my required 10. So now I've got an additional 8 electrons that I've got to put in my structure. So I'm going to put them in pairs of 2 around each nitrogen, so that now each nitrogen is going to have 8 electrons around it. That's 2, 4, 6, and 8. I'll do the same for the other oxygen. 2, 4, 6, and 8. I've satisfied the octet rule for both nitrogens, and I'm done. Do you agree that I'm done and my structure is good, is correct?
No, there's 14.
Right, I only need 10, but I've got 14, so I'm at my uh-oh moment again, but I already know what I need to do. So again, I'm going to take away 2 pairs, and then I'm going to replace those 2 pairs that I took away with another single covalent bond between the 2, making it a double bond. Do you agree that I'm correct now, or am I still wrong?
Still wrong,
Why am I still wrong?
because there's 12.
I have 12 and I only need 10. So what do? I do the same thing I just did. Second verse, same as the first. Take away 2 more lone pairs and replace those 2 pairs that I took away with another single bond between them. Now I have what type of bond between those 2 nitrogens?
Triple.
I have a triple bond now. Now is my structure good?
Yes.
Yes, I've got 10. 2, 4, 6, 8, and 10. Is each nitrogen happy?
Yes.
Yes. Each nitrogen is happy because each nitrogen has 8 electrons around it. 2, 4, 6 in the triple bond, and then the 2 lone pairs around each gives each nitrogen 8 total electrons around them. So each nitrogen is happy. So now, take 5 minutes. Go in your group rooms. Figure out ozone's Lewis structure based on everything that you've seen me do. Now I want you to try to figure out ozone on your own. And it's okay if you don't get it totally right, because I'm not expecting you to get it totally right. I'm expecting you to get it almost totally right. So take a few minutes, work on ozone, and then come back in the general room at the latest, about 2 minutes after 12. And then we're going to talk about ozone and why it's so special, why its Lewis structure is a little bit more special than O2 and N2. So just follow the rules. I've gotten you started. We know that we need 18 total. So we just put the 3 oxygens next to each other, connect them with a single bond. So I've put in 2, 4 of the required 18 already, and I'm going to let you pick up from there. Okay. So I am done with my ozone Lewis structure. Is my structure correct?
No.
Oh my goodness. My structure is incorrect. So can you help me fix it?
Erase 2 of the lone pairs. And then add another double bond on one side.
Okay, so you're saying I can erase 2 from the center, the central oxygen, and one of the other oxygens, right?
Yeah.
So if I erase here and here, then I would need to do just like we did before, put a double bond here, correct?
Uh-huh.
So now am I correct? Now is my structure good?
I think so.
I agree. So we do our count, 4, 6, 8, 10, 12, 14, 16, 18. Very good. And each oxygen is happy. Do you agree? Does each oxygen have 8 electrons around it?
Yeah.
Yes. But what if I would have done this? Would my answer still be correct? If I would have drawn it like this? If, in other words, if I would have taken the electrons from the central oxygen and the oxygen on the right, instead of taking the 2 electrons from the oxygen on the left, would I still be correct with my double bond over here on the right instead of on the left? Do you agree that I could have written this either way?
No.
Is this guy here correct?
No.
Why not?
I don't know. I just feel like I should say no.
Does anyone think that if on a test, if I drew this structure here for ozone's Lewis structure, would I be counted correct or incorrect?
Correct. I think.
Correct. What if I drew this one here? Would I be correct or incorrect?
They're both right.
They're both correct. You know why? They are called resonance structures. So we can draw 2 equivalent Lewis structures. They call them resonance structures. Both of these are correct. The molecule has 2 correct Lewis structures that you can draw. Then those 2 correct structures that are equivalent to each other, they are the same exact thing. They're called resonance structures. And so to denote that, we'll put both pictures, both Lewis structures, and we'll put a double arrow between them. So this one with the double bond on the right, the other Lewis structure with the double bond on the left, they're both correct. And they're called resonance structures. And so what that's saying is at any given time, the double bond can be over here, or the double bond can be over there on the right. And so what we really call them is a hybrid structure. And so I can draw a dashed line. And so we would call this here a single bond, right? And this bond, of course, is a double bond. But since we've come up with all types of nice chemistry analytical tools like X-ray crystallography and IR spectroscopy and NMR spectroscopy, they've been actually able to capture the picture of ozone on a molecular level using spectroscopic techniques. And what they found was this to be the actual structure, this hybrid. Because at any given time, that double bond can move from one side to the other. So what they call this bond, this hybrid bond, is a 1.5 bond. Is midway between a single bond and a double bond. So it's called a 1.5 bond or a 1.5 bond. And so if you can draw two equivalent Lewis structures, then they're called resonance structures, which are basically a hybrid structure. And so we've talked about single bonds, double bonds, and triple bonds. Now we also have the hybrid bond, or the 1.5 bond. So let's talk about strength of these bonds in relationship to each other, as well as length. So bonds are going to decrease in length as you go from single to double to triple. So a single bond is longer than a double bond, and a double bond is longer than a triple bond. The hybrid bond, the 1.5 bond, its length will fall between a single and a double. So a 1.5 bond is a little longer than a double bond, but it is shorter than a single bond. So we can put the hybrid 1.5 bond right in there. And then as far as the bond strength increases as you go from single to double to triple. So the triple bond is the strongest. Double bond is the next strongest. And then the hybrid bond, the 1.5, its strength is in the middle between a single and a double. So ozone, we drew our little hybrid bond there. So for ozone, the actual oxygen-oxygen bonds have properties that lie smack in the middle between that of a single and a double. And so we have that hybrid 1.5 bond. And so now that we've taken a look at Lewis structures, and we have a better understanding now of the differences between oxygen and ozone, both as how they exist in the troposphere versus the stratosphere. Now we know the difference in their molecular formulas, O2 and O3. And now we also know the difference between their Lewis structures. Oxygen has a double bond. Ozone has a 1.5 bond strength. So now do we understand why UVB doesn't get absorbed by oxygen, but just by ozone? So what we're saying is UVB strong enough to bond in oxygen? No, it's not. So UVB radiation only is strong enough to break the 1.5 hybrid bonds in ozone. So UVB gets absorbed by ozone because it's strong enough to break the bonds in ozone. UVC is the strongest of the UV radiation, and it's strong enough, it has enough energy to break both the double bond in O2 and, of course, the 1.5 bonds in ozone. So that dangerous UVC has two molecules that can absorb it and stop it from reaching the troposphere because it's the most dangerous of the three UV types. It has the most energy due to it having the highest frequency. So now we get a better understanding based on the Lewis structures of oxygen and ozone why ozone can only absorb the weaker energy UVB and not the UV, and why the UVB can only be absorbed by ozone and can't be absorbed by oxygen, because the UVB doesn't have enough energy to break the double bond in oxygen. And then we know UVA is the weakest of all three types of UV's radiation. And it's not strong enough in energy to break bonds in either oxygen or that 1.5 hybrid bond in ozone. That's why all of UVA reaches our troposphere. And that's what makes it so dangerous. And the major threat of skin cancer is UVA, because it's not strong enough to break any of the bonds in oxygen or ozone. So it reaches the troposphere. But UVB and UVC, all of the UVC gets knocked out by oxygen, ozone, and the stratosphere. UVB is not strong enough to break the bonds in oxygen. So it only has ozone we only have ozone as a protector in the stratosphere from UVB. That's why some UVB actually makes it to the troposphere, because the oxygen doesn't get broken down by UVB, because UVB is not strong enough to break that double bond in oxygen. And so the Chapman cycle is a set of reactions, which we call a reaction mechanism, that occur naturally in our stratosphere. And that's how we get a steady state or constant concentration of ozone in the stratosphere. Because you may say, wait a minute now, you're saying that UVC and UVB break the bonds in ozone? Then won't we run out of ozone? Well, no, because of the Chapman cycle. It's a set of reactions that allow us to replenish the ozone that gets broken apart by UVC and UVB radiation. And so you have these sets of reactions: oxygen, its double bond gets broken by UVC radiation with wavelengths that are less than 242 nanometers. And that bond gets broken, and what results is 2 oxygen atoms. These new oxygen atoms are fed into the Chapman cycle, and a single oxygen atom will react with oxygen and produce ozone. And then ozone will also react with a single oxygen atom, and then you get oxygen produced. And so therefore, just like the oxygen and ozone being used up in the cycle when the UV radiation, both UVB and UVC, break bonds in oxygen and ozone, the cycle has a way of reproducing those molecules. So therefore, in the stratosphere, we don't run out of oxygen in the stratosphere. You don't run out of ozone in the atmosphere because of this Chapman cycle. And it's cyclic. It always is continuously happening. So every time that UVC, UVB radiation destroys ozone, the Chapman cycle reproduces it. And that's how we stay protected from UVB and UVC radiation, is by the Chapman cycle. And so we're going to end lecture for today. And what I want you to do before Wednesday's class is take a look at these section 3.8 questions. And it's going to just give you some more practice with structures. Before I started class today, that's what this little note here is about. There's a question. I think it's Piper here today. There's a question on your, no, she's not in today. There's a question on your chapter 3 quiz 2 that's coming up with an error. It's not showing you the pictures that you need in order to answer the question. So I was on the phone with McGraw-Hill right before our class started. I've got a case number with their technical support. They're supposed to fix the question, but I've taken that question out, and so you shouldn't get that question. And I think only one of you guys in this section had already started that chapter 3 quiz too. And so, but that question has been thrown out. It's going to be replaced by another question, but hopefully they'll work on fixing that. And that may be a question that may show up on the midterm, for example. So I want to get that question fixed, but you won't have to worry about that question as far as chapter 3 quiz 2, because I've already thrown it out for now, because it was coming up an error, not showing the pictures that you need to answer the question. But before Wednesday, see if you can finish questions 1 and 2. And question 2 gives you some more practice in drawing Lewis structures, and be on the lookout for resonance hybrid structures, for those compounds that may have 2 equivalent correct Lewis structures. Okay, if you have any questions, you are free to stay after class, and I'll be happy to answer your questions. Just keep in mind that we're going to finish up chapter 3 on Wednesday. We have a little bit more to talk about in chapter 3, mainly the hole that was created in our ozone layer, because we were talking about the Chapman cycle, keeping our ozone levels constant. But we lovely humans were doing some things back in the 50s and 60s and 70s that was destroying our ozone and upsetting this natural Chapman cycle balance. So we're going to talk about what was done to destroy a part of our ozone layer. And once we figured out, oh gosh, we got a problem here, what have we done internationally as an international community to try to fix the problem? And so we'll talk about those things, those last little pointers on Wednesday. When we come in, we'll go over these questions. So make sure you try to draw as many of these Lewis structures as you can. And if you get stuck on one, that's fine, because you'll know what you don't know. You'll have some questions ready on Wednesday. So have a good rest of your Monday, and I will see you again in class on Wednesday. And again, make sure that you take advantage of the free chemistry tutoring in getting ready for your midterm that will be due on Sunday night. Have a good rest of your day.